Hello, dear friends. This is the Quasaria channel, and today we have a truly captivating journey into one of the greatest mysteries of modern astrophysics ahead of us. We'll talk about a question that sounds deceptively simple. Why don't galaxies fly apart? It would seem what could be simpler. There's gravity, it holds everything together, and that's that. But when scientists in the 20th century began studying this question in detail, they encountered something completely incredible. It turned out that galaxies should have flown apart billions of years ago, but they don't. And the reason that astronomers discovered turned our entire understanding of the universe upside down. Today, we'll learn the story of one of the most dramatic discoveries in the history of science: the discovery of dark matter. We'll talk about brilliant scientists who weren't afraid to challenge established ideas, about observations that left physicists stumped, and about how humanity realized it lives in a universe where 95% of the content is invisible to our eyes. Make yourself comfortable, grab a cup of tea or coffee, and let's begin this amazing journey through space and time. Before we delve into the problem, let's understand what a galaxy is and how it's structured. Understanding the structure of galaxies is critically important for our entire story. A galaxy is a gravitationally bound system consisting of stars, star clusters, interstellar gas and dust, dark matter, and, as we now know, other components. The sizes of galaxies vary from dwarfs containing just a few billion stars to giants with trillions of stars. Our home galaxy, the Milky Way, belongs to spiral galaxies. This means it has a flat disk with beautiful spiral arms, a central bulge called the bulge, and a spherical halo of old stars surrounding the entire system. The diameter of the Milky Way's visible disk is about 100,000 light years. For comparison, light travels from one edge of our galaxy to the other for 100,000 years. The Milky Way contains, by various estimates, from 200 to 400 billion stars. Imagine that number. If you started counting stars and named one star every second, it would take you more than 10,000 years to count them all. And this is just one galaxy out of approximately 2 trillion galaxies in the observable universe. All these stars are not in a static state. The galaxy rotates. Our Sun, located at a distance of about 26,000 light years from the galactic center, moves at a speed of approximately 220 kilometers per second and completes a full orbit around the galactic center in roughly 225 to 250 million years. This is called the galactic year. During Earth's existence, our planet, together with the solar system, has orbited around the galaxy's center about 20 times. What makes this giant carousel rotate? Gravity. More precisely, the gravitational attraction of the galaxy's entire mass. At the center of our galaxy, as in the centers of most large galaxies, there's a supermassive black hole. In the Milky Way, this black hole is called Sagittarius A star, and its mass is about 4 million solar masses. But even this giant black hole is only a tiny fraction of the galaxy's total mass. Most of the galaxy's visible mass is concentrated in stars. There's also interstellar gas, mainly hydrogen and helium, from which new stars form. There's dust, tiny solid particles creating those dark bands we see in photographs of galaxies. All of this is ordinary matter, or as it's also called, baryonic matter. And so, it would seem everything is clear. We have stars, gas, dust, a black hole in the center. Gravity from all this holds the galaxy together. What could be simpler? But this is precisely where our detective story begins. Our story begins in 1933. Swiss astronomer Fritz Zwicky worked at the California Institute of Technology and studied galaxy clusters. A galaxy cluster is a gravitationally bound group of galaxies, something like a city of galaxies, where instead of individual houses, entire galaxies. Zwicky studied the Coma cluster, or the cluster of galaxies in the constellation Coma Berenices. This is a rich cluster containing more than 1,000 galaxies. Zwicky measured the velocities at which individual galaxies move within this cluster. How do you do this? Using the Doppler effect. The Doppler effect is a change in wave frequency for an observer moving relative to the wave source. You've probably noticed it in everyday life. When an ambulance approaches you, the siren sound is higher, and when it moves away, lower. The same thing happens with light. If a light source approaches us, its spectral lines shift toward the blue end of the spectrum, blue shift, and if it moves away, toward the red shift. By measuring the red and blue shifts of spectral lines in light from different galaxies in the cluster, Zwicky could determine their velocities. And here he was in for a surprise. The galaxies were moving very fast, at speeds on the order of 1,000 kilometers per second. This is an enormous speed. For comparison, Earth moves around the Sun at a speed of about 30 kilometers per second. Zwicky understood physics. If galaxies are moving so fast, their kinetic energy is enormous. To hold them together in a cluster, corresponding gravity is necessary. And gravity depends on mass. Zwicky calculated how much mass there should be in the cluster to create sufficient gravity to hold such fast-moving galaxies. Then he tried to estimate the visible mass of the cluster. He counted the number of galaxies, estimated each one's mass by its luminosity. Bright galaxies are usually more massive, and got a number. And this number turned out to be too small, 50 to 100 times smaller than required. Zwicky faced a choice. Either his calculations were wrong, or the laws of physics don't work as we think, or there's a huge amount of matter in the cluster that we don't see. Being a bold scientist, Zwicky chose the third option. In his 1933 article, he introduced the term dunkle Materie, dark matter, Zwicky wrote in German. He suggested that a large amount of invisible matter must exist in the cluster, creating additional gravity. This was a revolutionary assumption. Essentially, Zwicky was saying, most of the universe consists of something we cannot see. For the 1930s, this sounded too radical. The scientific community treated Zwicky's idea with great skepticism. Many thought that most likely there were some errors in observations or calculations. Maybe there are many dim stars and clusters that we simply don't notice, or there's more intergalactic gas than we think. The idea of dark matter was shelved for several decades, but the problem didn't disappear. And 40 years later, it returned with new force. Let's jump to the 1960s and 1970s. American astronomer Vera Rubin, together with her colleague Kent Ford, began a systematic study of spiral galaxy rotation. And it was this work that became a turning point in dark matter history. Vera Rubin was an outstanding scientist, but her path in science was not easy. At that time, women in astronomy had to face significant prejudice. When Rubin was a student in 1948, she wasn't allowed to use the Palomar Observatory. Women simply weren't admitted there. But this didn't stop her. She continued to work, and her research ultimately changed our understanding of the universe. In the late 1960s, Rubin and Ford began a detailed study of the Andromeda Galaxy, our nearest large galactic neighbor, located at a distance of about 2.5 million light-years. They used a new, very sensitive spectrograph developed by Ford, which allowed measuring rotation velocities with high precision. What exactly were they measuring? They observed spectral emission lines from gas in the galaxy at different distances from its center. By measuring the Doppler shift of these lines, they could determine at what speed gas rotates around the galaxy's center at a given distance. Now, let's remember the solar system. Planets closer to the Sun rotate faster than distant planets. Mercury races around the Sun at a speed of about 48 kilometers per second, Earth about 30 kilometers per second, Jupiter about 13 kilometers per second, and distant Neptune only about 5 kilometers per second. This is a direct consequence of Newton's law of universal gravitation. If mass is concentrated in the center, as in the solar system, where 99.86% of mass is in the Sun, the rotation velocity of objects should decrease with distance proportionally to the square root of distance. This is called Keplerian rotation. In galaxies, mass is not distributed like in the solar system. Most stars are in the disk, not only in the center. Therefore, it was expected that within the disk, rotation velocity would first increase, because with increasing distance from the center, the number of stars inside the orbit grows, then reach a maximum, and beyond the visible disk begin to fall, as in the solar system. After all, beyond the disk there are no more stars, meaning mass no longer grows and velocity should decrease. But Rubin and Ford saw something completely different. They constructed a so-called rotation curve, a graph of rotation velocity versus distance from the galaxy's center. And this curve turned out to be flat. Rotation velocity reached a certain value and remained approximately constant even at enormous distances from the center, far beyond the galaxy's visible disk. This was completely unexpected. A flat rotation curve meant that the galaxy's mass continues to increase with distance, even where we don't see stars. In other words, some kind of invisible mass must exist, distributed in a huge halo around the galaxy. The first reaction was skeptical. Maybe this is a peculiarity only of Andromeda? But Rubin was persistent. She and her colleagues began systematically studying other spiral galaxies. One after another, dozens of galaxies showed the same pattern, flat rotation curves. This was not an exception, but a rule. Let's understand what this means physically. For an object to move in a circular orbit, gravitational attraction must provide the necessary centripetal force. If velocity is constant at all distances, this means gravitational force per unit mass must also remain approximately constant with distance, which, in turn, means linear mass growth with distance. But we don't see this mass. The galaxy's luminosity falls with distance. The number of stars decreases, but gravity somehow remains. Rubin was able to estimate how much invisible mass there should be. It turned out to be at least 5 to 10 times more than visible mass. Some galaxies showed even more dramatic ratios. It turned out that most of the galaxy is invisible. Let's now examine in more detail the physics of why galaxies should have flown apart without additional invisible mass. This is a key point for understanding the entire problem. Imagine you've tied a stone to a rope and are spinning it over your head. The stone moves in a circle thanks to rope tension, which provides centripetal force. If you spin the stone faster, rope tension increases. If the rope isn't strong enough, it will break and the stone will fly off tangentially. In a galaxy, gravity plays the role of the rope. A star at the galaxy's edge rotates at a certain speed. This creates centrifugal force. More precisely, this is an inertia effect. The star wants to move in a straight line, which tends to throw the star out of the galaxy. This is counteracted by gravitational attraction of all mass located closer to the galaxy's center. For a stable circular orbit, these two forces must be in exact equilibrium. But even if we consider that mass in a galaxy is distributed in a disk beyond the disk, where there are no more stars, velocity should still decrease. After all, for a star rotating far from the center, all the galaxy's mass is inside its orbit, and this mass no longer grows with increasing distance. When Vera Rubin measured real velocities, they turn out to be too large. At a distance, say, 50,000 light-years from the center, where there are almost no visible stars, gas rotated at the same speed as in the galaxy's central regions. This meant that centrifugal force there is enormous. Calculations showed if the galaxy had only the mass we see, stars and gas at the periphery would move so fast that gravity would be insufficient to hold them. They should fly away into intergalactic space. The galaxy should lose its edges, become smaller, evaporate. Moreover, if you calculate the time it would take for the galaxy to completely fall apart under such conditions, it's only a few 100 million years, a very short time by cosmic standards. But we see galaxies that are billions of years old, and they perfectly preserve their structure. The only reasonable explanation: galaxies have additional mass that doesn't emit light but creates gravity. And this mass must be distributed in a huge spherical halo extending far beyond the visible disk. It's precisely the gravity of this halo that keeps the galaxy's outer parts from flying apart. As scientists studied the problem more deeply, it became clear that dark matter is not some marginal correction to our models. It's a fundamental component of the universe, and moreover, a dominant one. Let's look at the numbers. When astrophysicists calculated how much dark matter is required to explain galaxy rotation curves, astonishing results emerged. In a typical spiral galaxy like the Milky Way, the ratio of dark matter to visible matter is approximately 10:1. That is, for every kilogram of stars, gas, and dust, there are 10 kilograms of invisible dark matter. But that's not all. Let's expand the scale and look at the universe as a whole. Cosmologists use several independent methods to estimate the universe's composition, and they all give consistent results. The first method is observations of relic radiation. This is radiation left over from the Big Bang, a kind of photograph of the infant universe when it was only 380,000 years old. The Planck Space Telescope measured with the highest precision tiny temperature fluctuations in this radiation. Analysis of these fluctuations allows determining cosmological parameters, including the density of different types of matter. The second method is studying the large-scale structure of the universe, the distribution of galaxies and galaxy clusters. The third is observations of distant supernovae, allowing measurement of the universe's expansion history. All these methods lead to the same picture. The modern cosmological model, called lambda-CDM, lambda-cold dark matter, gives the following composition of the universe. Ordinary baryonic matter, approximately 5%. Dark matter, approximately 27%. Dark energy, approximately 68%. Think about this. Everything we've ever seen, everything that makes up stars, planets, gas clouds, and ourselves, is only 5% of the universe's total content. dark matter makes up more than a quarter of the universe, meaning there's approximately 5 to 6 times more of it than ordinary matter. And what is dark energy, which makes up the largest part? This is an even more mysterious substance responsible for the accelerated expansion of the universe. But this is a topic for a separate, no less fascinating conversation. An amazing picture emerges. We, humans, made of atoms, live in a world where 95% of the content is of a completely different nature. We're a rarity in the universe. Baryonic matter is a small admixture in an ocean of dark matter and dark energy. Inside galaxies, the situation is even more dramatic. If you take a typical spiral galaxy and weigh, it turns out that approximately 90% of the mass is dark matter and only 10% is stars, gas, and dust. In dwarf galaxies, the ratio can be even more extreme. Sometimes for one part of visible matter, there are 100 parts of dark matter. This invisible mass is not concentrated in the galaxy's center. It forms a huge spherical halo extending far beyond the visible disk. If our eyes could see dark matter, galaxies would look completely different, like huge diffuse spheres, inside which small bright disks of visible stars seem merely decorative. Galaxy rotation curves are striking, but not the only evidence of dark matter's existence. Over decades of research, numerous independent proofs have accumulated, and they all point to the same thing. First, galaxy clusters. Remember Fritz Zwicky and his 1933 work? His observations were confirmed and repeatedly strengthened by modern research. Galaxy clusters contain enormous amounts of hot gas that shines in the X-ray range. By measuring this gas's temperature, one can estimate how deep the cluster's gravitational potential well is, and therefore its total mass. Result: mass is 10 to 100 times greater than the mass of visible stars and gas. Second, gravitational lensing. Einstein's general theory of relativity predicts that massive objects curve space-time, and this curvature affects light's trajectory. A light beam passing near a massive object deflects. This is called gravitational lensing. When we observe distant galaxies whose light passes near a massive galaxy cluster in the foreground, we see that images of these distant galaxies are distorted. They're stretched into arcs. Sometimes multiple images of the same galaxy are visible. By analyzing these distortions, one can precisely calculate how much mass the lens cluster contains and how this mass is distributed. The result is always the same. Mass determined by lensing is significantly greater than visible matter's mass. And what's especially important, the gravitational lensing method doesn't depend on assumptions about matter's state or laws of gravity. It directly measures mass through its gravitational influence on light. One of the most impressive examples is the so-called bullet cluster. This is a system of two collided galaxy clusters located at a distance of about 3.7 billion light-years from us. When these clusters pass through each other at enormous speed, something interesting happened. Ordinary matter in clusters is mainly hot gas. When the clusters collided, this gas interacted with itself, collided, and slowed down. We see this in X-rays. Two large regions of hot gas are in the system's center where the collision occurred. And where is the system's center of mass? It can be determined by gravitational lensing. And it turns out that the mass centers are not at all where the gas is. They're shifted to the sides, where the galaxies themselves are located. What does this mean? Dark matter, unlike ordinary gas, almost doesn't interact with itself. When the clusters collided, dark matter passed through the collision almost unimpeded, like two clouds of pellets flying through each other. It didn't slow down, but continued moving with the galaxies. This observation is very difficult to explain with modified gravity, which we'll talk about, but it naturally follows from the idea of dark matter as a separate substance. The bullet became one of the most convincing proofs of dark matter's real existence as a separate substance. But dark matter's role is not limited to individual galaxies' stability. It turned out to be a key player in forming the entire structure of the universe we observe. Let's return to the early universe. In the first moments after the Big Bang, matter and radiation were in a state of hot, almost homogeneous plasma. Almost homogeneous, but not completely. Quantum fluctuations in the very early universe created tiny density inhomogeneities, regions that were slightly denser or slightly more rarefied than average. These fluctuations were incredibly small. Deviations were only 1 part in 100,000. We can observe these primordial inhomogeneities by studying relic radiation. When the universe was 380,000 years old, it cooled enough that electrons could combine with protons, forming neutral hydrogen atoms. At this moment, the universe became transparent to radiation. Photons stopped constantly scattering on free electrons and began freely propagating in space. These photons we observe today as relic radiation. On the relic radiation map, we see tiny temperature fluctuations, hotter and colder spots. These spots reflect those very primordial density inhomogeneities. Denser regions had slightly deeper gravitational potential wells, and photons exiting them lost slightly more energy, becoming slightly colder. Over time, gravity amplified these inhomogeneities. Denser regions attracted surrounding matter to themselves, becoming even denser. Less dense regions, conversely, lost matter. This is a process of gravitational instability predicted back in 1902 by British physicist James Jeans. But here's the problem. Ordinary matter in the early universe couldn't quickly form structures. Why? Because it strongly interacted with radiation. Until the moment of recombination, when neutral atoms formed, baryons were tightly bound to photons through electromagnetic interaction. Radiation pressure prevented baryon matter from collapsing into denser structures. This is like if you try to mold a snowball, but wind constantly blew snow off your hands. Even after recombination, ordinary matter retained significant velocity due to the thermal motion it had in the epoch of coupling with radiation. These velocities prevented structure formation on small scales. If there were only ordinary matter in the universe, structures would form too slowly. In the 13.8 billion years of the universe's existence, those tiny primordial fluctuations wouldn't have had time to form the galaxies and galaxy clusters we observe. And here's where dark matter enters the stage. Dark matter doesn't interact with radiation. It doesn't feel photon pressure. Dark matter particles could freely move under gravity's action alone, experiencing no resistance. This means dark matter began forming structures much earlier than ordinary matter. Already in the early universe, when ordinary matter was still locked in plasma, dark matter began clumping together under gravity's action. These clumps created gravitational potential wells, invisible wells in space. When recombination finally occurred and ordinary matter was freed from radiation's influence, it began flowing into these already made gravitational wells created by dark matter. Dark matter essentially created an invisible framework, a skeleton, on which the visible universe was built. This process can be compared to building construction. Dark matter is the load-bearing framework of steel beams, and ordinary matter is the walls, windows, and finishes that attach to this framework. Without the framework, the building cannot stand. Modern computer simulations of the universe's evolution confirm this picture. When astrophysicists run supercomputer models including dark matter, they get a universe structure strikingly similar to what we observe. Filaments and walls of galaxies surrounding huge voids, hierarchical structure where small galaxies merge to form large ones, and those gather into clusters and superclusters. If you run a simulation with only ordinary matter, the result is completely different. The structure is too diffuse, too smeared, not at all like the real universe. So we know dark matter exists. We know how much of it is in the universe. We know how it's distributed in galaxies and clusters. But we still don't know the main thing. What is it made of? This is one of the most fundamental open questions in modern physics. What particles form dark matter? Decades of research have given us a list of properties that dark matter must have. First, it must be dark, that is, not emit or absorb electromagnetic radiation, light, radio waves, X-rays, etc. If it interacted with photons, we'd see it. Second, it must be stable or at least have a lifetime greater than the universe's age. If dark matter particles decayed quickly, it would no longer remain. Third, it must be cold. That is, particles must move slowly, much slower than the speed of light, at the moment of structure formation. This is necessary for dark matter to be able to gather into sufficiently compact clumps. Hot, dark matter, whose particles move at near light speeds, couldn't form small-scale structures. Fourth, it must interact very weakly with ordinary matter. Otherwise, we'd have already detected it in laboratory experiments. Scientists have considered many possible candidates for the role of dark matter. Let's go through the main ones. The first thing that comes to mind, maybe it's just ordinary objects that don't emit enough light. For example, black holes of various masses, brown dwarfs, objects too small to become stars, rogue planets not tied to stars, white dwarfs, remnants of dead stars, neutron stars, cold gas and dust. Such objects from ordinary matter receive the name macho, massive compact halo objects. They can be attempted to be detected using gravitational microlensing. If such a dark object passes between us and a distant star, its gravity acts as a lens, briefly amplifying the star's brightness. In the 1990s, several large observational programs were conducted, MACHO, EROS, OGLE, that tracked millions of stars, searching for such microlensing events. Result? Microlensing events were indeed observed, but there were too few of them. Analysis showed that machos can constitute only a small fraction of dark matter, no more than 20%, and only in a fairly narrow mass range. Besides, there are serious theoretical constraints on the amount of ordinary baryonic matter in the universe. These constraints follow from the theory of primordial nucleosynthesis, the process of light element formation in the first minutes after the Big Bang. The ratios of hydrogen, helium, deuterium, and lithium amounts in the universe are very precisely predicted by theory and depend on baryon density. Observed ratios indicate that there are approximately as many baryons as we see, those same 5% of the universe's total density. Consequently, dark matter cannot consist of ordinary atoms. It's something fundamentally different. WIMPs, weakly interacting massive particles. For the last decades, the main candidate for the role of dark matter particles were so-called WIMPs, weakly interacting massive particles. The idea of WIMPs is very attractive because it naturally arises in some extensions of the standard model of particle physics, particularly in supersymmetry theory. Supersymmetry predicts the existence of an entire set of new particles, superpartners of known particles. The lightest of these supersymmetric particles could be stable and serve as an excellent dark matter candidate. WIMPs should have a mass on the order of 10 to 1,000 proton masses and interact with ordinary matter through the weak nuclear interaction, one of 4 fundamental interactions in nature. The weak interaction is indeed very weak. It's much weaker than electromagnetic. That's precisely why WIMPs are so difficult to detect. The beauty of the WIMP hypothesis is that it offers an elegant explanation for the amount of dark matter in the universe. Calculations show that if WIMPs exist with the proposed properties, then in the early universe approximately as many should have formed as needed to explain the observed dark matter density. This is called the WIMP miracle. Simply an amazing coincidence. Axions. Another popular candidate is axions. These are hypothetical particles that were proposed in the 1970s to solve a completely different problem in particle physics, known as the CP violation problem in strong interaction. But it turned out that axions could also be dark matter. Unlike WIMPs, axions should be very light. Their mass could be trillions of times smaller than a proton's mass. But there should be incredibly many of them. If axions exist, then every cubic centimeter of space contains billions of axions, forming something like an invisible condensate permeating all space. Axions interact extremely weakly with ordinary matter, even weaker than WIMPs. But there's one possibility to detect them. In a strong magnetic field, an axion can sometimes turn into a photon. Experiments searching for axions use super strong magnets and try to register these rarest transformations. Sterile neutrinos. Neutrinos are real particles we already know. They're produced in huge quantities in nuclear reactions in the sun and other stars, in supernovae, and even in Earth's atmosphere when cosmic rays collide with air atoms. Every second, trillions of neutrinos pass through your body without interacting. Known types of neutrinos are too light and too fast, hot, to be dark matter. But physicists assume that other types of neutrinos may exist, called sterile neutrinos. They would interact even more weakly than ordinary neutrinos and could be much more massive. With certain parameters, sterile neutrinos could explain dark matter. Primordial black holes. Another interesting possibility is primordial black holes. These are black holes that could have formed not from stellar collapse, but in the very first moments after the Big Bang, from density fluctuations in the early universe. Such black holes could have various masses, from tiny microscopic to thousands of solar masses. If they exist in sufficient quantity, they could constitute a significant part of dark matter. Primordial black holes attracted special attention after LIGO, Laser Interferometer Gravitational Wave Observatory, began detecting black hole mergers. Some of the detected black holes turn out to be quite massive, which made some scientists wonder, couldn't these be primordial black holes? However, there are serious constraints on how large a fraction of dark matter primordial black holes can constitute, especially in certain mass ranges. These constraints follow from various observations, including microlensing, effects on relic radiation, and others. If dark matter exists, can it be detected directly? Physicists worldwide are trying to do this. and three main approaches to the search have been developed. Direct detection. The idea of direct detection is simple. If our galaxy is immersed in a dark matter halo, then dark matter particles must constantly pass through Earth and through us. Earth moves around the sun moves through the galaxy, and this motion creates a kind of wind of dark matter particles. Imagine you're riding a motorcycle in the rain. Even if rain is falling vertically down, from your point of view, drops fly at you from ahead because of your motion. The same with dark matter. Because of Earth's motion through the dark matter halo, a particle flux is created. Estimates show that billions of dark matter particles pass through every square centimeter of Earth every second, if these are WIMPs of standard parameters. But they interact incredibly rarely. A dark matter particle can pass through Earth like a bullet through fog, almost not noticing it. But almost never doesn't mean never at all. Very rarely, maybe once in several days or weeks, a dark matter particle can collide with an atomic nucleus in a detector. In such a collision, the nucleus receives a small recoil, it shifts slightly, and this tiny transferred energy can be attempted to be registered. Sounds simple, but in practice it's incredibly difficult. The problem is that there are many other processes that can cause similar signals. Cosmic rays, natural radioactivity in detector materials and surrounding rocks, even radon in air, all this creates a background against which one must search for the rarest signal from dark matter. To reduce background, direct detection experiments are placed deep underground. For example, the xenon experiment is conducted in the Gran Sasso Laboratory in Italy, under a mountain at a depth of 1,400 meters. The LUX Zeppelin (LZ) experiment is located in the former Homestake gold mine in South Dakota, USA, at a depth of 1,480 meters. The Chinese Panda X experiment is located in the Jinping Laboratory at a depth of 2,400 meters. This is the deepest underground laboratory in the world. The rock layer above the detector protects from cosmic rays. Detectors are made from ultra-pure materials with minimal radioactive impurity content. They're cooled to extremely low temperatures, sometimes almost to absolute zero, to reduce thermal noise. Many experiments use noble liquids, liquid xenon or liquid argon. When a particle interacts with a xenon atom, a light flash occurs and electrons are knocked out. By detecting both light and electrons, one can distinguish a signal from dark matter and background events. Over the last 20 years, the sensitivity of these experiments has grown thousands of times. But so far, no convincing signal from dark matter has been detected. There are several intriguing hints, but all of them either weren't confirmed with more careful verification or weren't reproduced by other experiments. What does this mean? This doesn't mean dark matter doesn't exist. This means that if dark matter exists in the form of WIMPs, then it interacts with ordinary matter even more weakly than we thought. Or dark matter is not WIMPs, but something else. Indirect detection. The second approach is indirect detection. The idea here is, if dark matter particles can annihilate with each other or decay, they should produce ordinary particles that we can register. Imagine, two dark matter particles meet and annihilate, turning into a pair of ordinary particles. For example, a quark and antiquark, or lepton and analepton. These particles then decay or interact, producing a cascade of other particles, including gamma quanta, neutrinos, positrons, and protons. Where is the probability of such annihilations highest? In places with high dark matter density, in galaxy centers, in galaxy cluster centers, in dwarf satellite galaxies of the Milky Way, which are believed to consist almost entirely of dark matter. Space gamma-ray telescopes, such as the Fermi Gamma-ray Space Telescope, scan the sky searching for excess gamma radiation from these places. On Earth, experiments like AMS, Alpha Magnetic Spectrometer, on the International Space Station search for unusual ratios of particles and antiparticles in cosmic rays. Have there been successes? There were intriguing findings. For example, AMS detected an excess of high-energy positrons in cosmic rays. This could be a signal from dark matter annihilation, but it could also be explained by astrophysical sources such as pulsars. In the Milky Way center, the Fermi telescope observed excess gamma radiation, which some researchers interpreted as a possible signal from dark matter. But other explanations, including a population of thousands of millisecond pulsars, can also explain the observations. The problem with indirect detection is that astrophysical backgrounds are very complex and poorly known. It's difficult to say with confidence, this is definitely from dark matter and not from some ordinary astrophysical process. Collider searches. The third approach is attempting to create dark matter in a laboratory. If dark matter is some new particle, maybe we can produce it by colliding ordinary particles at very high energies. The most powerful machine for this is the Large Hadron Collider, LHC, at CERN on the border of Switzerland and France. This is a ring with a circumference of 27 kilometers in which protons are accelerated to almost the speed of light and collide with energies up to 13 to 14 trillion electron volts. How to search for dark matter at a collider. Dark matter particles, if they're produced in a collision, will immediately fly out of the detector without leaving a trace. They don't interact with ordinary matter in detectors. But one can search for missing energy and momentum. By conservation laws, total energy and momentum before collision must equal total energy and momentum after. If we see that some ordinary particles appeared in the detector, but when calculating energy and momentum something is missing, this could be a sign that part of the energy was carried away by invisible particles, possibly dark matter. The LHC has been actively searching for such events for more than 10 years. Some interesting anomalies were discovered, but nothing convincing so far. The LHC's most famous discovery, the Higgs boson in 2012, confirmed the Standard Model, but didn't reveal that new physics that could indicate dark matter particles. Especially anticipated was supersymmetry, which predicts many new particles, including dark matter candidates. But so far the LHC hasn't found any signs of supersymmetric particles. This doesn't completely exclude supersymmetry. Perhaps superpartners are too heavy for LHC energies, but enthusiasm for the simplest versions of supersymmetry has waned. To be fair, not all physicists agree with dark matter. Alternative explanations of observed phenomena exist, and the main among them is modified gravity. The basic idea is, what if the problem isn't that we don't see something, but that we incorrectly understand gravity? Maybe gravity laws don't work quite as Newton's or even Einstein's theories describe, especially under certain conditions. The most famous modified gravity theory is MOND, Modified Newtonian Dynamics, proposed by Israeli physicist Mordechai Milgrom in 1983. Milgrom noticed an interesting pattern. Problems with galaxy rotation curves arise where gravitational acceleration becomes very small, on the order of 10 to minus 10 meters per second squared. This is billions of times smaller than free fall acceleration on Earth. Milgrom suggested, what if at such small accelerations Newton's second law, force equals mass times acceleration, stops working in its ordinary form. What if the relationship between force and acceleration changes at small accelerations? He proposed a modified formula and showed that with its help one can explain flat galaxy rotation curves without invoking dark matter. Moreover, Milgrom's formula contains one new fundamental constant of nature, that very critical acceleration, and this constant amazingly agrees with observations for many galaxies. MOND indeed works quite well for individual galaxies. It predicts observed rotation curves with astonishing precision. Moreover, it makes successful predictions in some cases where dark matter models require additional assumptions. But MOND has serious problems. First, this is not a full-fledged gravity theory, but rather a phenomenological formula. There were attempts to create a relativistic theory underlying MOND, for example, TeVis, tensor vector scalar gravity, but they're complex and have their own problems. Second, MOND works poorly for galaxy clusters. Even with modified gravity, there's not enough mass there. MOND supporters have to assume that clusters have some additional invisible mass. Usually they talk about neutrinos or other forms of ordinary matter, but then the advantage over dark matter is lost. Third, and this is most important, MOND cannot explain observations of the bullet cluster. Remember that system of collided galaxy clusters? They're the center of mass, determined by gravitational lensing, is not where the visible matter is. This is very difficult to explain with modified gravity, but naturally follows from the existence of dark matter as a separate substance. Fourth, MOND doesn't explain the formation of a universe's structure. Computer simulations with MOND don't reproduce the observed distribution of galaxies and large-scale structure. They also don't agree with detailed observations of relic radiation. Nevertheless, MOND continues to intrigue some physicists. Perhaps there's a grain of truth in it. Maybe both dark matter exists and gravity works slightly differently at small accelerations. Or maybe MOND's success for galaxies points to some important patterns in dark matter distribution that we don't yet fully understand. Other alternative theories exist. F, R, gravity, Verlin's entropic gravity, quantum gravity effects, and other exotic ideas. But none of them has yet been able to explain the entire spectrum of observations as well as the dark matter model. Even if we accept dark matter's existence, many mysteries and unsolved questions remain that astrophysicists are grappling with. Computer simulations of dark matter predict that in galaxy centers, dark matter density should sharply increase, forming a sharp peak or cusp. But observations of many galaxies, especially dwarfs, show that in their centers dark matter density is rather constant, forms a flat core. This discrepancy between theory and observations is called the cuspy core problem. Why does this happen? Perhaps ordinary matter, gas and stars, affects dark matter distribution more strongly than we thought. Supernova explosions, stellar wind, central black hole activity, all this can eject gas from the galaxy's center, and this motion can smear dark matter concentration. Or perhaps dark matter particles interact with each other slightly more strongly than we assumed. The missing satellites problem. Simulations predict that around a large galaxy like the Milky Way, thousands of small satellite galaxies should orbit. But we observe only several dozen. Where do the rest go? Perhaps they exist, but are too dim to detect. These are dark galaxies, almost entirely consisting of dark matter with a minimal number of stars. Modern telescopic surveys indeed find more and more very dim dwarf galaxies. Perhaps the problem will be solved when we learn to search for them better. Or, again, this may indicate that dark matter properties differ from the simplest cold dark matter model. For example, if dark matter is slightly warm, particles move slightly faster. Or if particles can interact with each other, this would suppress the formation of the smallest structures. The too big to fail problem. This is a related problem. Simulations predict the existence of fairly massive substructures in the Milky Way's halo. Such massive dark matter clumps should have captured enough gas to form bright satellite galaxies. But the Milky Way's brightest satellites, such as the Large and Small Magellanic Clouds, turn out to be less massive than simulations predict. These predicted massive substructures are sort of too big not to become galaxies, hence the problem's name. The dark matter disk problem. Some studies suggest that part of the dark matter in our galaxy may be concentrated in a thin disk, coplanar with the stellar disk, and not only in a spherical halo. If this is so, this would have important consequences for direct detection experiments. But the question remains controversial. Self-interacting dark matter. To solve some of the mentioned problems, physicists are considering models in which dark matter particles can interact with each other, but not with ordinary matter. Such self-interacting dark matter would behave slightly differently than completely non-interacting matter and could smooth out some sharp peaks in galaxy centers. Experiments and observations continue, and these mysteries will gradually become clearer. They remind us that our understanding of dark matter is still incomplete, and many discoveries lie ahead. So where are we today, almost 90 years after Zwicky's work, and what awaits us in the future? On one hand, evidence for dark matter's existence is incredibly convincing. Multiple independent observations, galaxy rotation curves, cluster dynamics, gravitational lensing, universe structure formation, relic radiation, all point to the same thing. Approximately 27% of the universe's mass energy consists of some invisible matter. On the other hand, this matter's nature remains a mystery. Despite decades of intense searches, a dark matter particle has not been detected directly. This is disappointing, but also means we're on the threshold of something truly new and unexpected. Searches continue, and they're becoming increasingly sophisticated and sensitive. In the field of direct detection, next-generation experiments with detector masses of tens of tons are being prepared. Xenon NT, LZ, Darwin. They will be tens of times more sensitive than existing ones. If WIMPs exist in the most likely parameter range, these experiments should detect them. If even these experiments don't find a signal, this will mean that either WIMPs interact even more weakly and even more sensitive detectors are needed, or dark matter is something completely different. Axion searches are also intensifying. Experiments like ADMX, Axion Dark Matter Experiment, Haystack, Organ, and others use different methods and investigate different ranges of possible axion masses. This is long and painstaking work because axion parameters can vary in an enormous range. At colliders, after the LHC upgrade, the high luminosity LHC will begin operating with higher luminosity, which will allow studying rare processes and searching for heavier particles. Future colliders are also planned, perhaps the International Linear Collider, ALC, in Japan, or the Future Circular Collider, FCC, at CERN with energies tens of times higher than the LHC. In orbit and on Earth, new telescopes are being prepared that will help study dark matter by indirect methods. The James Webb Space Telescope is already working and studying the earliest galaxies in the universe. Understanding how the first structures formed will help us better understand dark matter's role. The Vera Rubin Observatory, yes, named after that very Vera Rubin, will begin work in Chile. This telescope will conduct the deepest and widest sky survey, detecting billions of galaxies. By studying gravitational lensing on huge scales, so-called weak gravitational lensing, one can map dark matter distribution in the universe. Next-generation space gamma-ray telescopes, such as CTA, Cherenkov Telescope Array, will search for signals from dark matter annihilation with unprecedented sensitivity. Perhaps the breakthrough will come not from new observations, but from theory. Maybe a new idea is needed, a new look at the problem. Some physicists are exploring exotic possibilities. Dark matter may not be one type of particle, but an entire dark sector, with many different particles and its own interactions. A dark photon, dark atoms, even dark stars may exist. This would open an entire invisible world parallel to ours. Others are exploring connections between dark matter and other physics mysteries. Why is there more matter in the universe than antimatter? Why are neutrino masses so small? Maybe these problems are connected. Let's step back and think about the broader significance of dark matter's story. Once we thought Earth was the center of the universe. Copernicus showed this wasn't so. Earth revolves around the sun. This was the first great displacement of humanity from a central position in the cosmos. Then we learned that the sun is just one of hundreds of billions of stars in our galaxy. Second displacement. Then it turned out that our galaxy is just one of trillions of galaxies in the observable universe. Third displacement. The discovery of dark matter is the fourth, and perhaps the most radical displacement. It turns out we're made not only of unusual material, atoms, but this material constitutes only a tiny fraction of the universe. We're a rarity, an exception, not the rule. On the other hand, this discovery shows the amazing power of the scientific method. We cannot see dark matter directly. We can detect it only indirectly through its gravitational influence. And nevertheless, using mathematics, physics, careful observations, and logic, we were able not just to suppose its existence, but to determine how much of it is in the universe, how it's distributed, what properties it must have. This resembles detective work. The criminal left the crime scene, but left traces. A good detective can reconstruct much about the criminal from these traces: his height, weight, where he was, where he went. So we, studying dark matter's traces, its gravitational influence, reconstruct its properties without even seeing it directly. Dark matter's story is also a lesson in scientific humility. It teaches us that the universe is stranger and more amazing than we can imagine. It reminds us that our intuitive ideas, based on everyday experience, can be deeply incomplete. Who would have thought that most of the universe is invisible? This contradicts all our experience. But observations are irrefutable, and science forces us to accept this amazing reality. At the same time, this is a source of hope and inspiration. We live in an era when one of nature's greatest mysteries is still unsolved. Perhaps in the coming years or decades, a discovery will be made that will enter history textbooks. Perhaps some of the young people listening to this will participate in this discovery. You might ask, why is this important? How does dark matter affect our everyday life? After all, it almost doesn't interact with ordinary matter. Can we simply ignore it? The answer is multilayered. At a practical level, understanding dark matter is critical for understanding the universe's evolution, galaxy formation, and ultimately the emergence of conditions for life. Without dark matter, galaxies, stars, planets, and we ourselves wouldn't exist. At an intellectual level, this is one of nature's fundamental mysteries. Humanity has always strived to understand the world around us. This striving is part of what makes us human. At a practical technology level, the history of science shows that fundamental research often leads to unexpected practical applications. When Einstein developed general relativity, he didn't think about GPS navigation, but without accounting for relativistic effects, GPS wouldn't work accurately. When physicists studied quantum mechanics, they didn't foresee transistors, computers, and smartphones. Technologies developed for searching for dark matter, ultra-pure materials, ultra-sensitive detectors, cryogenic systems, data analysis methods are already finding application in medicine, security, and other fields. So we've taken a long journey. Let's remember where we began. Why don't galaxies fly apart? The answer we have today: they're held together by gravity. Not only the gravity of visible stars and gas, but mainly the gravity of dark matter. This mysterious substance, which is 5 to 6 times more abundant than ordinary matter, which we cannot see, which almost doesn't interact with us, but which is absolutely necessary for galaxies' existence, the universe's structure, and ultimately ourselves. We learned about amazing scientists, Fritz Zwicky, who first dared to suppose dark matter's existence, Vera Rubin, whose careful observations proved this wasn't just an outlandish idea, but our world's reality. About thousands of other researchers who continue to unravel the cosmos' secrets. We learned that the observable universe is just the tip of the iceberg. Below the visible surface lies a huge, invisible world that we're only beginning to understand. 95% of the universe consists of dark matter and dark energy, substances whose nature we haven't yet comprehended. We learned about the heroic efforts of physicists worldwide who build detectors deep underground, launch space telescopes, create the most powerful supercomputer simulations, trying to catch the elusive signal from dark matter, or at least better understand its properties. And we learned that the mystery is not yet solved. After almost a century of research, we know that dark matter exists, where it is, how much there is, what role it plays. But we still don't know what it's made of. This is one of the greatest unsolved problems in science. Perhaps the answer will be found tomorrow. Perhaps in 10 years. Perhaps in 50. But sooner or later, thanks to humanity's persistence, ingenuity, and curiosity, this mystery will be unraveled. And when this happens, it will be a moment of human mind's triumph. A moment when we touch one of the most fundamental truths about our universe. Meanwhile, galaxies continue to rotate, held together by dark matter's invisible embrace. Billions of stars follow their orbits, not suspecting that most of the mass governing their motion is invisible. And we, humans on a small planet near an unremarkable star on an ordinary galaxy's edge, continue to look at the sky, ask questions, and seek answers. Because this is what makes us human. This is what allowed us to journey from caves to space telescopes, from myths to mathematics, from fear of the unknown to a thirst for understanding. And this is what will one day allow us to unravel dark matter's mystery and answer the question, what is our amazing universe really made of? Thank you for being with us on this fascinating journey through one of modern science's greatest mysteries. Today we talked about why galaxies don't fly apart and learned that the answer to this simple question led us to discover an invisible world constituting most of the universe. This is the Quasarea channel, and we'll continue exploring the cosmos's mysteries together with you. If you enjoyed this episode, like it, subscribe to the channel, and definitely write in the comments about which cosmic mysteries you'd like to learn more about. Maybe about dark energy, or about black holes, about the possibility of life on other planets, or about time travel. Remember, every time you look at the night sky, you see only a tiny part of what's there. Most of the universe is hidden from our eyes, but not from our minds. And in this lies humanity's greatest adventure, the striving to understand the incomprehensible, to see the invisible, to know the unknowable. Until new meetings in a universe of knowledge, keep looking at the sky and asking questions. This is how great discoveries are made. Clear skies and new discoveries to you.